Alright everybody, welcome back to this video. This is the first video for section 9.2 of AP Calculus BC, second derivatives of parametric equations. So our whole goal in this video is to just talk about how we find the second derivative and go through a bunch of examples of finding the second derivative and how we can use it. And we'll start with developing the parametric formula for d squared y dx squared. Now, think back to when we were taking Cartesian derivatives, and when we had a function like dy dx is equal to, 5x squared, in order to take the second derivative of that, it was very simple because we just took the derivative with respect to x to get the second derivative. Now, a little bit of a difference with what we're going to have going on in this video. When we try to find the second derivative of a first derivative that was from a parametric curve, we've got a curve that looks like this. And so if I took the derivative of this with respect to x, I would get d squared y dx squared is equal to 10t, and then applying the chain rule, dt dx. And so in order to get this second derivative, I have a second factor in here that needs to actually take place. So since I take the derivative of this expression with respect to t, in order to get this expression with respect to t, I need to take and multiply this by dx dt in order to make it equivalent to d squared y dx squared. And so let's take a look at what this formula actually looks like. It's a little bit different than just going ahead and taking the derivative straightforward, because we want to take a derivative with respect to x when we've got t's in the equation. And this is the easiest way to view it, finding the second derivative, our parametric formula for the derivative. If we know dy dx, and we know that dx dt does not equal 0, to find the second derivative, we'll get the second derivative is equal to, and in order to get the second derivative, we're going to take the derivative with respect to x of our first derivative. Okay? It's a standard Leibniz definition of the second derivative. But when we take this derivative of dy dx, since dy dx is a function of t, it's easiest for us to take the derivative of that with respect to t. But if we're going to take the derivative of this with respect to t, we need to also take the derivative of this with respect to t, which leads us to our formula, that in order to get the second derivative d squared y dx squared of a parametric function, we're going to take the derivative of dy dx with respect to t, and then we're going to divide it by dx dt. So there's an extra step, an extra layer here in finding the second derivative of a parametric curve when we're finding d squared y dx squared that we need to make sure that we apply. And I'm going to try and utilize a method here that encourages you, like I kind of go through the same steps every time I do this, that hopefully will encourage you to do this correctly. So let's go ahead, and we're going to go ahead and find our second derivative. We're starting with two curves. I'm going to go ahead and cut myself off some space here. So we'll start by finding dy dx. That's always the first step in finding the second derivative, is make sure we have the first derivative. So we find dx dt. The derivative of this is going to be 2/3 t. And then I'm going to find the derivative of this, dy dt. And that's equal to 1 over 2 square root of t. And so I'm going to go ahead and find dy dx. And dy dx is equal to 1 over 2 square root of t divided by 2/3 t, which is the same thing as 1 over 2 square root of t times the reciprocal of this, which is 3 over 2t. So simplifying this, we end up with 3 over 4 t to the negative 3 halves. as our value for dy dx. Okay? Now, in order to find the second derivative, I'm going to do two things. I'm not going to just go ahead and write d squared y dx squared and go ahead and do that right away. What I'm going to do is I'm going to take the derivative with respect to t of dy dx, which hopefully if you write it this way, it reminds you that the derivative we're finding here is not d squared y dx squared. So I'm going to take the derivative of this with respect to t, and the derivative of 3/4 t to the negative 3/2 with respect to t is going to be negative 9/8 t to the negative 5/2. And now, to find the second derivative, d squared y dx squared, that's going to be equal to the derivative with respect to t of dy dx divided by dx dt. So it's going to be equal to negative 9/8 t to the negative 5/2 divided by 2/3 t. So our second derivative here is going to be equal to negative 9/8 t to the 5/2 times the reciprocal of this, which is 3/2t. So this becomes negative 27/16 t to the 7/2. And that is our second derivative, d squared y dx squared, for this parametric curve. All right, let's go ahead. We'll do the same thing in part B. We're going to find the second derivative in terms of t. And so first I find dx dt. It's going to be negative 2 sine of t, and dy dt is going to be 3 cosine of t. So dy dx is equal to 3 cosine of t over negative 2 sine of t, which is negative 3/2 cotangent of t. I'm certainly welcome to simplify that to help me take the derivatives of things. And then we'll go from here. We're going to take the derivative with respect to t of negative 3/2 cotangent of t. That's going to be negative 3/2 times the derivative of cotangent is negative cosecant squared of t. And so this is equal to positive 3/2 cosecant squared of t. So then d squared y dx squared is going to be equal to the derivative of dy dx, which we just found, divided by dx dt. So it's going to be equal to 3/2 cosecant squared of t divided by negative 2 sine of t. And that's going to be negative 3/4. And dividing by sine is the same as multiplying by its reciprocal, and its reciprocal is cosecant. So this ends up being negative 3/4 cosecant squared, of t. That's a big deal. Make sure you have the right variable in there. And there's our second derivative. All right. I'm going to go ahead and cut this video off here, and we'll come back and do a second video for this lesson where we do a few more examples of finding the second derivative. Only in those examples we're going to go ahead and apply them. All right. See you then. Have a great rest of your day, and bye-bye now.